today I'm going to tell you about work that I've been doing with my PhD student, Tiago França, on binary black hole mergers in some alternative theories of gravity, which is called Horndeski theory. Right. Right. So yesterday, Franz Pretorius gave an excellent talk, which basically motivated everything, and in particular our work. So most of what I'm going to say now is just repeating what he already said yesterday, but I'll just say it again, just to stress the main points, which is that we are in the era of gravitational wave astronomy. Now, gravitational wave detectors can measure gravitational waves produced in mergers of compact objects, such as black holes. And this is a great opportunity for theorists, in particular, because this offers us the possibility to test gravity in the strong field regime in a novel way. And potentially, these can lead to a more profound understanding of gravity itself at the classical level, and who knows if something more. So as Franz stressed yesterday, the current data indicates that the deviations from general relativity are small. So all current observations are compatible with GR, and no significant deviation has been observed. But this shouldn't mean that this shouldn't deter us from pursuing this program of trying to test general relativity in the strong field regime, even if these deviations are small, because we've been promised that the forthcoming generation of detectors, in particular the space-based gravitational wave detector, should be able to carry out precision measurements of gravitational waves. So it is conceivable that in the not so far future, such small deviations could be detected. So, however, there are some issues in carrying out this program of testing general relativity in using gravitational waves. And one is, as Franz pointed out, is that we need to extract predictions from alternative theories of gravity. The reason being that the signal is buried in the noise, and in order to extract the signal, one needs templates, and most of the current templates are based on general relativity. So if there's a waveform buried in the noise which doesn't come from general relativity, it may be difficult to extract. And related to this issue of extracting predictions of alternative theories of gravity is the fact that there is not just one alternative theories, but there are actually probably, hundreds. And they can be motivated from various ways. All these theories modified Einstein's gravity in some different way. As Franz pointed out yesterday, some of them modified the left-hand side of the equation by, for example, changing the geometry. For instance, derivative theories with higher derivatives. Some other theories modified the right-hand side by introducing extra fields. So all these theories have problems. So it's a bit like in Anna Karenina's opening sentence that all happy families are alike, but all unhappy families are unhappy in their own way. So all these alternative theories of gravity, each one of them suffers from a different type of problem. So it's at this moment, since we don't have a preferred theory, one cannot sort of focus on that particular theory and try to sort of make sense of it. So far, the approach has been, in a way, general. So we can try to extract as much information from various alternative theories of gravity without having to focus in one particular theory. And one of the main issues with many of such alternative theories of gravity is that they do not have, or it is not known whether they have a well-posed initial value problem, and in which case it's not clear whether they have predictive power. So one of the open issues in this program is there a way in which one sort of can make sense of these alternative theories of gravity and try to extract predictions from these theories, at least in a regime when they are supposed to be valid. And that's the approach that we are going to take today. So of course, these problems have been around for a while, and there are basically three ways forward. One way has been to find well-posed formulations of these some theories, and there's been very important progress in this area recently by Aaron Kovac and Harry Rial, which have found which have found a modified generalized harmonic gauge, such that a large class of theories that are quite popular turn out to be well posed in this case. And I mean, recently with my student, we generalized this to other gauges that are commonly used in numerical relativity. So at least there are some classes of theories that can be tested, at least in this strong field regime. Another approach, which has been carried out with success, is to linearize around general relativity. So since we know that the corrections to Einstein gravity are small, then it could make sense to just linearize around, say, a binary black hole background and try to incorporate the corrections from these alternative theories. And as I said, this program has been carried out to some success by various groups, but there are some issues with this approach, which I will comment on later. And another approach is by Louis Lenner and collaborators, who, inspired by the Mueller-Israel-Stewart formulation of relativistic hydrodynamics, they've proposed to fix these alternative theories by introducing auxiliary fields with that satisfy equations of motion that one has to prescribe ad hoc, which depend on some parameters, such that these auxiliary variables approach the physical variables in a given time scale. If one knew the microscopic theory, all these extra parameters should be given by the microscopic theory, but of course, we don't know that. So this approach has to be treated with care to make sure that one reproduces the correct long wavelength physics that we are interested in, and which is what these alternative theories are supposed to capture anyway. Louis Lenner gave a very nice talk in the first workshop of this program, so I will not comment on this approach anymore. So I will refer you to Louis's talk in the first workshop, where he explains this approach in detail. So, as I said, there are many theories, alternative theories. In this talk, we will focus on a particular class of such alternative theories, which are ones that contain high derivative correction to Einstein gravity. These particular type of corrections are well motivated from microscopic considerations. So if one takes, say, any theory of quantum gravity, such as string theory, and one computes the corrections to the Einstein-Hilbert Lagrangian, one can precisely compute those higher derivative corrections with concrete coefficient. So that's quite analogous to hydrodynamics, which can be understood as an expansion in derivatives of the various thermodynamic fields around thermodynamic equilibrium. And this series is supposed to be an infinite series. So in practice, we will just truncate this series, and this has some issues. But just to say that these high derivative corrections are quite generic and arise from, say, quantum gravity. Now, another motivation for such corrections is because they involve higher powers of the Riemann tensor, for instance, or other higher derivatives of the other fields. If one has other matter fields, then one may hope that in the strong field regime, such effects may be enhanced. So even if the coefficient in front of these terms in the action is small, because they involve higher powers of the curvature, then you may have a sizable effect. And just to be concrete, we will concentrate on studying black holes. The reason is that black holes are fundamental in any theory of gravity, and we can fully describe them within the theory. Other gravitational objects, such as neutron stars, typically require non-gravitational physics, which is often poorly known, or it's hard to model in practice. So if we want to learn about the, say, fundamental aspects of gravity, we will just focus on black holes. So the outline of the rest of the talk is as follows. So first, I will describe this cubic Horndeski theory, and I'll try to motivate why we chose this particular theory. And then I will explain what is the what we understand as a weakly coupled regime of this theory and how we can identify it, because this is the regime of validity of the theory, at least as a classical theory. And then I will show you some results that we've obtained about black hole binaries in such. In particular, we'll look at the waveforms that one obtained in these theories and compare them to general relativity. And I will finally conclude and outline some future directions. So even if I'm just virtually present here, so if you have any questions during the talk, just interrupt me. Okay, so what are these Horndeski theories of gravity? So Horndeski theory is the most general scalar tensor theory of gravity that can be derived from a diffeomorphism invariant action, which give rise to second order equations of motion. So this is like the scalar tensor analog of Lovell. So at least on the scalar sector, and is often written in terms of the sum of these 5 terms in the Lagrangian. The first term, L1, I don't know if you can see my, sorry, I don't know if you can see my pointer, but the L1 is, L1 is just the Einstein-Hilbert term, the usual scalar kinetic term, and an arbitrary potential, which depends on the scalar field itself and not its derivatives. And then the other terms, L2, L3, L4, and L5, can be understood as high derivative corrections in the scalar sector. So as the name suggests, the cubic theory corresponds to just considering the first 3 terms in this action. And the reason why we picked this particular theory is because for the cubic Horndeski theory, it had been shown by Aaron Kovac recently that it is well posed in the standard PSSN or CCZ4 formulation of the Einstein equations and the standard gauge used in numerical relativity, this singularity avoiding gauges. So we picked this theory just for convenience, because it made it easier to implement in our code. But we believe that some of the effects that we observe here should also apply to other Horndeski, more general Horndeski theories, as I'll explain. Just a comment is that the cubic theory, in this theory, matter naturally couples to gravity in the Einstein frame. So that's not the case if one considers, say, the quartic theory. In that case, one can argue that the natural frame to consider is the Jordan frame. But these issues with frames will not arise in what I'll have to say, as I'll explain later, because as far as the waveforms are concerned, in our setting, both frames will give rise to the same result. So the general Horndeski theory, which just consists in just considering the all terms in the action, has also been shown to be well posed in this modified harmonic gauge by Harvey and Aaron Kovac recently. Now, I'll just write again the cubic theory in its full Baroque glory, let's say. And it depends on these functions, G2 and G3. Sorry, I should have said earlier that these are arbitrary functions of their arguments. But if one wants to sort of do calculations, you have to make some choices. So in our work, we chose a massless scalar or a massive scalar. So that's just the standard potential for a mass term for a scalar. And then for G2, we made this particular choice, which Weinberg showed that this is the most general scalar term up to 4 derivatives that one can write. So from the point of view of effective field theory, which is the point of view that we will take in this talk, this is the general term that we can pick at this order in derivatives. And for G3, we just pick the easiest, most non-trivial, the easiest function one can consider in this case, and that's just made for convenience. But as I will argue our results, at least the results I will tell you about later, will not depend on these particular choices. And the main motivation for us to consider this theory is as a toy model to try to first learn what type of difficulties one may encounter when one considers theories with high derivatives, and also try to identify general effects that can be attributed to these theories. So here, the high derivatives are only in the scalar sector. The gravity sector is just standard Einstein theory. But as we shall see, some of the problems that arise should also arise in any high derivative theory of gravity. So in this case, in this sense, it's a useful model, and that's our main motivation. We did not choose this theory for phenomenological reasons. That's not the main purpose of our work, at least at this stage. Okay, so let me now discuss what I mean about the weakly coupled regime, because that's important in order to make sense of these theories. So in this talk, we will take an effective field theory approach, which is we understand these theories, Einstein gravity and this Horndeski theory, as from the point of view of effective field theory. So as I argued earlier, in general, one expects an infinite series of high derivative corrections coming from some more fundamental theory that we don't know. And we just take the first few terms in the action beyond Einstein. So this truncated theory only makes sense as such if these corrections to the Einstein-Hilbert term are small at all times. If that's not the case, then truncating this action to the first few terms is not justified, because on general grounds, we expect that the high derivative terms that we ignored to be as important, or if not more, than the ones that we've kept. So we can only make sense of what we're doing as long as these corrections to the Einstein-Hilbert action remain small. And this is compatible with the nonlinearity still being important. And as I said, this is consistent with neglecting the higher derivative terms in the action. And it is precisely in this regime where the corrections to the Einstein-Hilbert, and in this context of a scalar field, just a standard scalar field action, then it is only in this context that these theories have been shown to be well posed. And when these corrections are large, as we shall see shortly, then these theories are no longer well posed, at least in the gauges that, and in these formulations that we use here. And we'll see examples of these shortly. So in practice, in all our simulations, we will keep track of the weak coupling condition, which for us will be these dimensionless numbers that we have when one can construct from the couplings of the theories, G2 and G3, and a length scale that measures the size of the derivatives of, in this case, the metric and the scalar field. So we will demand that this combination, which is what appears in the equations of motion, in the terms that modify the two derivative terms from the standard Einstein-Hilbert plus scalar field action or equations of motion. So these are the coefficients that appear. So we want that those corrections to remain small at all times. If not, then we have to discard this theory. So even if these corrections are small, then one could take a perturbative approach and linearize this theory around Einstein's scalar field, let's say. But it is well known that doing so may lead to the perturbative series that breaks down due to secular effect in the regime where perturbation theory should still be valid. So that's something that we avoid by just treating these theories fully nonlinearly. But there's been some very interesting recent work by Leo Stein and Galvez Geresi, which they try to deal with these secular effects using renormalization group flow. But I will not discuss this here. And another point of considering these theories fully nonlinearly is that if we just linearize, then one may miss non-perturbative physics. And as Luis explained very well in his talk, That's an example of some non-perturbative physics that one may miss is in relativistic hydrodynamics, is if one does not take into account the viscosity terms, then one can, if you start from a turbulent regime, then you will never see laminar flow, for instance. Or another instance of this is in the nonlinear instability of ADS, where very sophisticated perturbative approaches have been proposed, but those approaches always fail right before black hole formation because the latter is a non-perturbative effect. So we want to make sure that even though the corrections to the Einstein-Hilbert scalar equations of motion are small, then we keep track of all relevant non-perturbative physics that may tell these theories apart from each other. So our first goal was to identify the weakly coupled regime of these Horndeski theories in the space of initial conditions and coupling. So what we want to do first is to consider scalar field collapse to form black holes. And these black holes of course, there will be a scalar cloud surrounding them. So we want to identify the regime in which this can happen, and yet the theory remains weakly coupled, because we will then use this as initial data for the binary. Now notice that, of course, we know that GR breaks down, for example, in the interior of black holes. And of course, these theories with higher derivatives will also break down. But here we'll take the approach that since we want to observe, say, gravitational waves far away from the black holes, we are not interested in the physics in the interior of black holes. So we'll just excise the interior of black holes whenever they form. Because if the UV behavior of GI is bad interior of black holes, then for these theories of higher derivatives is worse. So we are not interested in the interior of black holes, so we just excise. And that's okay, because in principle, information cannot escape black holes, at least classic. So the first thing that we did was to study, as I said, scalar field collapse in just assuming spherical symmetry for simplicity. And it turns out that in this setting, one can construct just a dimensionless number that measures the deviations from GR due to this Horndeski in the initial data. And these are these two theories, the L2 and L3. These are these dimensionless number, which will allow us to map the space of initial conditions and identify the weakly coupled region. So just to so why is this non-trivial? Because in this case, since in the scalar sector, the theory is a high derivative theory, then the metric that controls the propagation of the scalar mode is non-trivial. It's an effective metric. So the scalar modes do not propagate at the speed of light. So they have different characteristic speed. And as you can see, so these two effective metrics, the one on top is for the G2 theory, the one below is for the G3 theory, given our specific choices of these functions G2 and G3. The details are not important, but clearly one can perceive that these terms that are multiplied by these coupling constants are large, then the hyperbolicity of this metric need not be Lorentzian, for instance. And that's a signal that one enters the strongly coupled regime. Also, these effective metrics depend on the field and its derivative. So in general grounds, one would expect that shocks can form from smooth initial data, and then one would need a new criteria to uniquely continue the solution beyond these shocks. So these are all difficulties that will arise in any theory with higher derivative. Not just in the scalar sector, but also for the metric, for instance. And as I said, when the theory becomes strongly coupled, then hyperbolicity can break down. So just to give you an example of what can happen. So here we are monitoring, here I'm just showing scalar field collapse. These white lines just follow the peak of the Gaussians of the scalar field. Then here we're monitoring the determinant of this effective metric and these the time component with indices upstairs. This is just useful to keep track of the hyperbolicity of the theory. And this is just for a concrete value of the coupling constant G2. And so in these plots, we keep the coupling constant fixed, and then we change the amplitude of the scalar field. So to the left is small amplitude, and to the right is large amplitude. So for small amplitude, then the scalar field just collapses, and you can see very little deviations from GR. So I should say that for these quantities, the GR value is 1. So anything away from 1, either greater than 1 or smaller than 1, is deviation, signaling deviations from GR. So as we increase the amplitude of the scalar field, then the deviations from GR increase. And at some point in case 3 here, if the amplitude is large enough, a black hole forms. So in this case, we see that right before a black hole forms, then there are significant deviations from GR. But then once the apparent horizon forms, then all these deviations just are hidden inside the horizon. So this dotted line is the sound horizon of the scalar field. And notice that if the amplitude of the scalar field is large enough, then a big black hole forms. And in this case, the deviations from GR are very small on and outside this apparent horizon. But if one increases the value of the coupling constant, then all hell breaks loose, and the hyperbolicity of the theory breaks down, and that's why we could not continue these evolutions further. And this happens even before apparent horizons can form. So this would be an instance in which we would be trying to use the theory outside its regime of validity. And in this case, the initial data is weakly coupled, but the dynamics drives the theory into the strongly coupled regime. So what we wanted to do first is to identify precisely which regions of the initial conditions we could construct global solutions in this theory such that they remain weakly coupled throughout. So we run many simulations, and in the end, we just came up with these maps. I'm going to explain you what this is now. So here there is this black band. So this is the region near critical collapse. Understanding what it means for the theory to be weakly coupled near critical collapse is subtle. So that's because this was not our interest. So we just make sure that we stayed away from the region with critical collapse. So to the left is weak data. So that's initial data that does not form a black hole. And to the right, we have strong data where you form a black hole. So on both sides, the blue region is the region in the space of initial conditions and couplings, such that we can construct global solutions that remain weakly coupled throughout the evolution at all times. In the orange, well, this yellowish region, this is the region that in which even though the initial data is weakly coupled, then further in the future, the evolution of this data, the theory becomes strongly coupled and hyperbolicity breaks down. In the paper, we explain the details of what type of breakdown one can have, but that's not relevant for this talk. So here, the green region is the region where the initial data is strongly coupled, so we don't want to be there. And this white region to the right is the region where the initial data already contains a trapped surface. So since we were interested in studying gravitational collapse, then we also want to stay away from that region. So basically, the bottom line of this study is that in this blue region to the right, we can form black holes, and the theory remains weakly coupled at all times. So that's the region where we want to pick in order to construct consistent initial data for the binaries. So so once we've have identified the weakly coupled region, then we can go on and study binaries. Now, of course, these studies that we have done here are only for studying gravitational collapse. And of course, a binary just goes on for a while. So it's not at all obvious that the data that remains sort of weakly coupled when one does spherically symmetric scalar field collapse, then will also remain weakly coupled when one studies a binary. So that's something that we had to take into account. That said, when we studied gravitational collapse, we didn't assume, even though the initial data was chosen to be spherically symmetric for simplicity, our code did not assume spherical symmetry. So let me now explain, tell you about the binaries. So as initial data, we chose in both the G2 or the G3 theories, we chose a scalar field in this blue region, but in the strong data side, let's say when we form a black hole, we chose massless or massive scalar fields, and we chose massive scalar fields. I'm just going to show you now the results on massive scalars. The reason is that even though in these theories do not admit hairy black holes, even having a mass term in the scalar field allows for the scalar to remain in the vicinity of the black hole for longer. So if we were hoping to observe some deviations from GR, it seemed that it would be useful to consider these a mass term for the scalar, so that the scalar has more time to interact with itself and with the black hole. So we chose this initial data, which on its own is constrained satisfying. So we solve the full constraints, but then we superpose them. So that implies that our choice of initial data violates constraints. But we place the two lumps of scalar field that collapse far away. So the initial constraint violations due to the fact that we superpose the scalar lumps are small. So that's something that that we can monitor this initial constraint violation, and we keep track of it. And as I said, we make sure that the initial data is in the weakly coupled regime, and we chose the parameters such that the black holes that subsequently form from gravitational collapse describe 5 eccentric orbits. We chose eccentric orbits for 2 reasons. The first reason is that it was easier in the sense that it requires less fine-tuning of the initial parameters, but also they are more interesting for this type of studies. They are useful for this test of GR because in each of the close encounters of the 2 black holes in eccentric orbit, one has strong field dynamics. So it gives us more, say, a better chance, or you have the chance of like strongly interactions for longer in eccentric orbit. And we shall see this very clearly in the simulations that I'll show you in a second. And as I was saying, so here we make sure that at all time, this weakly coupled condition is satisfied. So we don't want large deviations from GR, at least locally. And yeah, we just excise the interior of black holes. And just to reemphasize that here, we just did the simulations in the just standard gauges used in numerical relativity. Okay, so now let me show you a movie that Tiago produced of one of these binaries in Horndeski theory. That's in the G2 theory. So here, these grayish things that you see are already the black holes. So I've just skipped the initial collapse part. So here you see the 2 black holes, and this bluish cloud is the scalar density that surrounds the black holes. And as you can see here, there's higher density near the black holes. And as the binary progresses, you will see also the gravitational waves that are emitted. So let me just run this movie. So as you can see, the scalar field just drags around the black holes. And in the first close encounter, we see the first burst of gravitational radiation. Then the second close encounter, there's another burst of radiation. And finally, then the black holes are now close enough so that they will merge. And it produces the final burst of radiation. And as you can see, there's some scalar field still surrounding the black hole, which will eventually, some of the scalar field will escape to time like infinity, and the other will, and most of it will end up being absorbed by the black hole. So just to give you just a close view of the binary at one instant. So here you see, again, the blue region is the scalar cloud surrounding the black hole. This orange circle is the apparent horizon, and this reddish part is the excised region. So we don't keep track of what's going on inside the black hole. So let me show you now one of the waveforms that we extract from this system, and that's for a particular choice of the scalar mass, 0.5, and one of the largest values of the coupling that we could simulate, ensuring that the theory remained weakly coupled. So one thing that, so these in these waveforms, so these initial wiggles that you see at around time 500, so this is the first burst of radiation that is produced in the first close encounter of the binary. So the initial constraint violations are basically so small that you can't see them in this plot. The second wiggle is the second close encounter, and just the final, and later on we see the final part of the waveform when the two black holes eventually merge. So one thing that seems to be generic from all our simulations of binaries in this theory is that there is a shift in the waveform compared to GR. So here what we did is we simulated the binary in Horndeski, and then we simulated the same binary again with a massive scalar in GR, without the Horndeski term. So the GR waveform is the green curve that you see here. So we chose the initial data so that the total ADM mass is the same for both simulations. And in this case, we see this a significant dephasing between the two waveforms. And this dephasing is large. I mean, it's not something which is proportional to the smallness parameter, say in the initial data. It's much larger. It's way larger, and it's like visible by eye. And this seems to be a generic effect. So here I'm just showing you another waveform for the G3 theory with slightly different values of the couplings. Of course, the theories are different and different signs. So again, in this case, the GR is the wave in the middle, and the Horndeski waves are the ones that you see on either side. So, of course, the details of the shift will depend on the strength of the Horndeski coupling and the sign. But in any case, we see this shift, and the important thing I want to stress is that this shift is large compared to the weakly coupled condition that we see at any given time. So I want to emphasize that that's so this weakly coupled condition tells us about the deviation from GR locally, but this dephasing is a global effect. So that's an instance in which a small effect can accumulate and over significantly give rise to a significant weakly coupled condition as a function of time for the first waveform that I showed, and these peaks that you see here, these are the close encounters, and finally there's a last peak that you see here is the last peak right before merger. There's something that puzzles me here, which is why the weak field condition, the weak couple condition, is not larger at the merger. But that's something we are analyzing, and may have to do with the way we compute it. But in any case, we compute it in various ways, and at least for these examples that we have that I'm just talking about here, it's always small. Doesn't matter how you compute it. So we are confident that this dephasing is a robust effect that we see in this class of theory. So I'm running out of time, so let me quickly wrap up and summarize. So we performed simulations in these cubic Horndeski theories. We think that this effect, this dephasing that we've observed, is generic. It doesn't depend on the details of our sort of peak of Horndeski theory. So in particular, it's something that one might expect to see in more general Horndeski theories, and maybe also in EDGB type theories. In this case, though, this theory admits hairy black holes, so there might be some other differences due to that fact. So what lies ahead? So as I said, our main motivation for this project was to study high derivative effect. And this was, in the Horndeski case, this was only in the scalar field, but we would like to now look at high derivative theories of gravity. And this is ongoing work with Ramiro Cayuso, Thiago, and Luis Lerner. And we just, in this case, we consider just the 8th derivative theory of gravity, which give rise to equations of motion with 4th order derivative. So the question is how one can make sense of this theory. And it turns out that following Luis's approach, then one can construct a well-posed version of this theory, which hopefully makes sense. So Luis mentioned this in his talk, so I refer you to his talk for more details. And as I said, so we also found generalizations of Kovac's and Real's construction for finding strongly hyperbolic versions of some theories of interest, in particular EDGB and Lovelock. And one can show that they're also strongly hyperbolic in these other gauges that are commonly used in numerical relativity. And so this opens the door now to study the nonlinear, the fully nonlinear regime of these theories in black hole binaries in large classes of alternative theories of gravity. So hopefully we will be able to start getting some ideas of what types of modifications theories with high derivatives give rise to, and maybe we can take out this effect in future gravitational wave detections from LIGO or other detectors. So that's it. That's all I have to say. Thanks for your attention.